I recently gave an illustrated talk to my local astronomy group. This video is based on that talk. The title is, How Big Is It? So it would be as well to clarify what I mean by it. It is that deep sky object that you're viewing in your telescope's eyepiece, or perhaps viewing or imaging with your camera. It's not any solar system object, but one much farther out into space. Its view might be clearly defined, or it might be just a faint fuzzy. Let's start by considering why we're asking the question, how big is it, in the first place? What do we want when we view or image an object? A pretty picture? Yes, of course we do. The prettier the better. Not only is it more pleasing to look at, but also the prettier it is, the more likely it is to display a lot of interesting detail. But is that all? No, really. We would soon tire of using our telescopes if that was the case. No, we also want to understand the nature of the object. That way, we give real meaning to our observing. So, what kind of information do we want? Well, for starters, what kind of object is it? Is it a galaxy, or a star cluster, or a diffuse nebula, etc., etc.? And then, of course, there is the background information that applies to that class of object. How did it originate? What is it made of? And what's its likely future? Then there is the matter of where is it in the sky? You may think that that's blindingly obvious. Clearly it's where our telescope is pointing when we're viewing the object. But there's more to it than that. It would be good to know where the object is in relation to us. For example, take the Orion Nebula, Messier 42. It's close to us in our own arm of the Milky Way galaxy. If you liken our galaxy to a big city, you could say that M42 is in our own back garden, or, if not, then at least in our neighbour's back garden. By contrast, the Lagoon Nebula, Messier 8, is located in the Sagittarius arm, the next one in towards the centre of the galaxy. In terms of our city analogy, it's in the next suburb towards the city centre. Thinking in those terms can help us to better locate the object in our mental map of the sky. How far away is it? We know that all deep sky objects are a long way away, so is it so important to know that this object is twice as far as that object, or maybe 3 times as close as some other object? Perhaps not, except insofar as the general rule applies, saying that the closer an object is to us, the bigger it will seem, and vice versa. Which leads us on to the last consideration in our list, how big is it? Let's just take a moment to consider these attributes and see which of them defines the object itself. What is it? Yes, obviously we need to know that, but the rest of the background information, while important and interesting for understanding its general nature, does not define the object itself. Where is it, and how far is it? Well, these are just matters that relate to us as viewers. They're not intrinsic to the object itself. So, if we remove the extraneous items from the list, we're left only with what is it, and how big is it? On that basis, knowing the size of the object becomes important in getting a true understanding of what we're looking at. I hope that you agree with me, as otherwise this is going to be a very short talk indeed. On the understanding that you do, and that we need to know the size of our object, how can we find out what that size is? What a silly question, you may say. Clearly, all we need to do is look it up in our source reference materials. But unfortunately, it's not quite so easy as that. You'll quickly find that those reference materials don't always give you what you want. In fact, size is not always quoted. Yes, you will get a linear size, for example as so many light years, for the very big and bright deep sky objects, but you don't have to go very far down the scale to smaller and dimmer objects before all you'll get is size quoted as an angular measurement. In other words, how big an angle the object measures in the sky. Take this article from Wikipedia, for example. It describes the spiral galaxy Messier 83. Now, for us Southerners, M83 is an important, big, bright galaxy that's quite easy to observe. And yet, while the article quotes M83's distance as 15.2 million light-years, it only gives its size as 12 and a bit minutes of arc. Now, I don't know about you, but for me, 12 and a bit minutes is rather meaningless. What I want to know is what its linear size is in light-years. You can imagine this little scene when you're showing M83 in your eyepiece to someone else, say at a public outreach session. You say that the galaxy is very far away and maybe you will quote the distance. And you say that even so, we can still see the galaxy, so it must be very big. You get asked, how big is it? And you reply, 12 and a bit arc minutes. You shouldn't be very surprised to get a blank look in response. No, what we want to know is that the size of M83 is 128,900 light-years. So, if we want to know the linear size, but we're only given the angular size, what can we do? Well, obviously, find some way to convert the angular size into its equivalent linear size. And how can we do that? Well, I'm afraid we'll need to delve into some boring stuff, math. But I do promise to keep it simple and short. As with many math questions, let's start with a diagram. Here in the middle is this little green dot representing us. And over on the right is a galaxy. We're surrounded by our sky, which we can represent by this circle, and the size of the circle is the distance to the galaxy. What do we know about the galaxy? We're given its distance and the angle that it measures in the sky. Let's add a couple of lines to the diagram. First, we'll join the ends of the two long lines where they touch the circle. This will create a triangle, and the new line will represent the size of the galaxy. Then we'll draw another line, cutting the triangle into two halves, so that we end up with two smaller, back-to-back right-angled triangles. Now, if you remember your high school math, you'll know that if you start with a right-angled triangle, and you know the size of one of the other two internal angles, like angle A here, you can easily calculate the size of the side opposite the angle, here side S, by using the formula sine A multiplied by D, where D is the length of the longest side of the triangle. Applying that to our problem, D is the distance to the galaxy, and A is 1/2 of the galaxy's measured angle. Remember that we have here two back-to-back right-angled triangles, each of which contains 1/2 of the galaxy's measured angle. So you can probably see that the size of the galaxy is twice the sine of 1/2 of that measured angle multiplied by the distance to the galaxy. The line that we have drawn as representing the length of the galaxy is really just the chord of the arc of sky along which the galaxy lies. Should we not rather be measuring the length of that arc? After all, that's where the galaxy is, like this. Well, okay, we'll have to go back to school again. We should note that in our diagram, the distance to the galaxy is the radius of the sky circle that we have drawn. Now, when we know the radius of a circle, we can easily calculate the circle's circumference, the distance all the way around the outside of the circle. To do that, we use the formula 2 multiplied by pi, which is about 3 1/7, multiplied by the length of the radius. Of course, once we know the length of the circumference, we can easily calculate the length of any arc by first dividing the circumference by the 360 degrees that there are in a circle, and then multiplying the result by the number of degrees, or part degree, that defines the arc. So, we have two methods for converting an angular measurement into its equivalent linear size. We can use the sine function to calculate the length of the chord, or we can use the pi function to calculate the length of the arc. Which one should we use? Consider this table of two columns. On the left, I've listed various angles of arc, starting with the biggest at the top and ending with the smallest at the bottom. So we move down from 10 degrees of sky through 5 degrees, 1 degree, a half a degree being 30 arc minutes, 1 arc minute, and ending up with 1 arc second. The second column lists the extent of the difference between the two methods of calculation for each of those angles. This difference is expressed as a percentage of one of the methods used. It doesn't matter which one, and the precision is given to 1/1000th of a percentage point. As you can see, nothing appears in this difference column until you get to an angle of 1 degree of sky, when the difference is 1/1000th of a percent. And even at an angle of 10 degrees of sky, the difference is only about 1/8 of a percent. Now, let's consider the size of the deep sky objects that we are concerned with. Definitely, they will measure less than 10 degrees of sky. Almost certainly they'll measure less than 5 degrees of sky. And very probably, most will measure less than 1 degree of sky. So you can see that for the objects that we're concerned with, the difference between the two methods of calculation is so infinitesimally small that we can ignore it, and either method is just as good as the other. Putting all that together, we can say that if we know the distance to an object and the measured angle for that object, and we remember the appropriate math formula, and we have a calculator that has a sine function and or a pi function, we can calculate the linear size of the object. Or we can use software to do the job for us, in which case we won't have to remember the math. When I was looking at this problem a few years ago, I first thought that it would be easy to locate suitable software by looking on the internet. But I just didn't find what I was looking for. Maybe I didn't look hard enough. Maybe I didn't look in the right places. But at the end of the day, I didn't find anything. So I got to thinking, how hard could it be to create a little calculator to do the job? After all, the underlying math is very simple. So I did just that, and the result was astrosize, which I'll use here from time to time. Now please don't think that this talk is about astrosize. It's just a convenient tool I'll use here. For the basic calculations that we've been talking about, a simple calculator having a sine or a pi function will do just as well. Perhaps at this stage, it's as well to remind ourselves of the size of the problem. I always think of it as being like a three-legged stool. One leg is the distance to the object, the second leg is the angular size of the object, and the third leg is the object's linear size. If we know the value of any two of the legs, the math that we've been looking at should allow us to calculate the value of the third leg. In our case, we know the distance and the angular measurement, and we want to calculate the linear size. Here's a screenshot of the software, and I have to admit that it's not particularly glamorous. Not to put too fine a point on it, it's positively drab. But then it's only a calculator, and it does at least display the three legs of the stool: the distance, the angular measurement, and the linear size. Here's an image of the Statue of Liberty Nebula in the constellation of Carina in our southern skies. It lies some 9,000 years distant. We want to determine the size of the statue, including the smoky flames arcing around and above it, and we're told that they measure 30 arc minutes of sky. Like this, about the size of the full moon in the sky. Right, let's bring in astrosize and enter the 9,000 light years that we're given. Okay, the angular size is 30 arc minutes,
and we'll press the calculate button and we get a return value of 79 light years for the size of the object. In other words, the size of the statue and its smoky flames from top to bottom, like so. Right, let's clear the decks and we'll put astrosize away.
Okay, so far we have found our object's linear size either by getting it directly from our source reference or indirectly by converting a given angular size. But what if the reference source just quotes the object's distance without giving any indication of its size? For the smaller, dimmer deep sky objects, that can often be the case. How can we get to the linear size then? Well, we'll need to take a two-stage approach. Firstly, we should determine the object's angular measurement, and then, having got that, we can convert it into the required linear size. So, how can we determine the angular measurement? The simplest way to do that is to use your sky atlas. For example, if you use a bound paperbook atlas like Uranometria, you'll know that it includes a number of transparent plastic overlay sheets with black grids drawn on them. Having found the page showing the object to be measured, you select the appropriate plastic overlay and use the grid lines to measure the object's angular size. It's a bit clunky, but it does work. But these days you're more likely to use a computerized sky atlas such as Stellarium shown here. In that case, you'll probably find that the software includes a measuring tool. Stellarium does. You simply drag your mouse over the atlas display and the software reports the angle that you have just traversed. Maybe you use a tablet, such as an iPad, to display your sky atlas, in which case you may well be using Sky Safari. It too has a measuring tool that you can use to determine the object's angular size. Or maybe astrosize can help. Well, yes it can, provided that you have an on-screen image of the object and you know some angular property of or in the image. Let me show you what I mean. Let's go back to the Statue of Liberty Nebula image that we saw before. It's an image that I took myself, and I know that the combination of telescope and camera that I used produces an image with a field of view measuring 58 minutes 32 seconds vertically and nearly 1 minute 19 minutes horizontally. Remember that the nebula is 9,000 light years away. With just that information to hand, can we determine the linear size of the statue?
Bringing back astrosize, re-enter 9,000 light years as being the distance value. We'll turn to the measure page and the value for the vertical height of the image, 58 minutes 32 seconds, we'll enter in as our base angle here, 58 minutes 32 seconds. Now we need to tell the software what 58:32 seconds looks like in the image, so we'll use the calibration or base circle. We'll color it green, thicken up the edge, and we'll increase and move it so that it just spans between the top and bottom edges of the image. That's probably about right. Okay, now we need to turn to the measure circle, which we'll colour yellow, and we'll thicken that up a bit, and now we'll move and size the measure circle so that it just fits over the statue and its flames. Move it a bit, and up there maybe, increase its size. It's getting about right. Okay, we'll move it. down a little bit, maybe back. It's looking a bit tight, maybe just a little bit larger. That's, don't want to be too finicky. That's about right. Okay, now I don't know if you've noticed, but the software is telling us that we've just drawn the yellow circle to measure 30 minutes and 5.6 arc seconds, which is, as near as damn it, the 30 minutes that we used before. Copy that across to the calculate page, and we again get a value of 79 light years for the statue, like so. Right, let's clear some of the information from astrosize. I'll just zero out these figures here. I don't want to clear it completely, as you'll see why in a minute, but I'll just hide the circles and put the software away.
Here's an image of some galaxies in Virgo. Down at the bottom is Messier 87, which is a giant elliptical galaxy, and it's usually described as being some 120,000 light-years across, quite a bit bigger than the Milky Way. You may recognize the line of galaxies at the upper right as being Macarian's chain. Those of you who were here at last month's meeting will remember that Dr. Lee Spittler gave an excellent talk about his Huntsman project for assembling a compound telescope using a number of large Canon lenses, each attached to an imaging camera. His object is to image the very faint outer parts of galaxies that don't normally show up in their images. And he used this field of galaxies to illustrate what he's aiming at. Here, an image of the sort that he aims to produce has been superimposed over the normal view. It was taken by an equivalent deep imaging telescope in the Americas. And this was the example image that Dr. Spittler showed us, showing how large the galaxies actually are. At that point in the meeting, someone asked how large Messier 87 is as displayed. There was some discussion on the point, and some figures were suggested, but without coming to a definitive answer. So what do we know about this image? We're given that it spans 2¼ degrees. With that in mind, and from our earlier discussion tonight, you'll recognize that in order to measure M87, all we need to know is its distance. And that's easily found out as being 54 million light-years. Not all of M87 is shown in this image, but if we measure the top half at, say, 0.81 million light-years, and double that, we arrive at a value for the whole galaxy of 1.6 million light-years. So, if you're here tonight and you asked the question last month, you now have your answer, 1.6 million light-years. At this point, let's step back and summarize where we've got to. We've determined that to properly understand a deep sky object, we really need to know its size. And one way or another, we should be able to find out that size. But where does that get us? Having found out the object's size, what can we do with that knowledge? Well, maybe we can start down that road by looking at this image of the Swan Nebula, Messier 17. It lies in the constellation of Sagittarius and is 5,500 light-years away. First of all, let's determine the size of the bright part of the nebula in this area here, and to do that we'll bring it back, astrosize, and we'll use it as we did before. Now I know we've gone through this process already, but please bear with me. I'll enter in 5,500 light-years as the distance, and since this is an image that I took myself and it was taken with exactly the same imaging camera telescope system as the one that we used for the Statue of Liberty Nebula, the calibration process for that should apply equally well to this one too.
So we can check that and we'll see, and yes, it does. Fine, so we can hide the calibration circle and simply turn to the measure circle and use that to determine the size of this bright part of the nebula over here, and we'll need to increase it a bit. Something like that, maybe. Yes, that's about right. Okay, I'll copy that value over to the calculate page, and it returns a size value of 56 light years. So, this one nebula, that bright part of it, is 56 light years across. Let's pause a bit and think about what 56 light years means. What does it mean to you? Yes, it's a big figure. It's 56 times the 9.5 trillion kilometers that there are in a light year. So maybe intellectually we can get a reasonably good feeling for what 56 light years means, but do you really have a gut feel for it? Well, it's difficult, isn't it? Maybe we can compare it with something that's a little bit more familiar to us, maybe closer to home. So let's do that, and the software I'll use gives us an extra page called the compare page, and it lists various objects that we could use as comparisons, and the most obvious one to take in this particular case is the distance to Alpha Centauri, the nearest star system beyond our solar system, and it's at, we can say, 4 light years away from us. Okay, the program has drawn a little green hatch circle over the image, and in the middle of the circle is a little yellow dot, and that represents the Sun, or if you like the solar system, or again if you like us. And the radius of the circle is 4 light years at the scale of the image that we're looking at. Now, we don't really need these labels here, so I'm going to get rid of the labels, and we don't really need the measure circle either, and so I'm going to hide that. And now we're simply left with this compare circle that has a radius of 4 light years. Does that help you get some better feel for what the 56 light years of the Swan is? Well, maybe. Maybe it would help if we moved the Sun, the solar system, or us if you like, into the middle of this dark cloud here. And if we did that, and we were located there, then all of the dark cloud, and in fact just about all of the bright part of the Swan's neck, would be closer to us than is our closest star, Alpha Centauri. Or maybe if we were to put ourselves into the middle of these bright, hot, class O, BA stars here, these are the powerhouse stars that are illuminating the whole of the nebula, then all of those, or maybe nearly all of those stars, would be closer to us than is Alpha Centauri. So our night sky would be full of very bright stars indeed. Now, does that give some better indication as to what the full size of the nebula is here, the 56 light years? Well, I'll leave it to you to decide, but it certainly helps me. Right, well, we've used AstroSize as much as we need to tonight, so I'll simply put it away and we'll carry on.
Here's an image that should be familiar to you. It is, of course, the inner part of the Eta Carina Nebula. It's also an image that I took. So I know that as imaged, the nebula spans 170 light years. And of course, I was able to measure the size of any smaller part of the nebula too. Like, for example, the small complex of dust pillars indicated here by the yellow arrow. You can see that I've included an enlargement of the region so that you can see it more clearly. It turns out that the dust pillars measure 5 light years from end to end. Now, so far in this talk, we have been considering object sizes of 79 light years for the Statue of Liberty Nebula, 56 light years for the Swan Nebula, and 170 light years for this image of the Eta Carina Nebula. So 5.4 light years is really quite small and insignificant, right? Well, let's think about that. Let's remind ourselves that 1 light year is about 9.5 trillion kilometers. It might help to get a better grasp on how long 5.4 light years is if we were to consider how long it would take us to travel that far. Currently, or at least at the time when I was preparing this talk, the fastest vehicle that we have created is the Parker Solar Probe, which hurtled in towards the Sun at 688,000 kilometers per hour. If we were to travel at that speed, a journey of 5.4 light years would take us 8,472 years. If we were to end that journey today, we would need to have started out long before the pyramids were built. But I'm sure that you're thinking, we're an inventive species, clever monkeys if you like, and our technology is not going to remain at today's level. We can expect that we will be able to go faster in the future. Well, how fast a speed do you think we could possibly achieve in the foreseeable future? I'll leave it to you to decide what we might mean by foreseeable future. 5 times today's limit? 10 times? 10 times would be 6.8 million kilometers per hour, which is nearly 7 million. So what say we be generous and round that up to 10 million kilometers per hour? Can I suggest that we go one step further up to 10.8 million kilometers per hour? I do that because 10.8 million kilometers per hour is just about 1% of the speed of light. It's hard to comprehend a man-made object travelling at 10.8 million kilometers per hour, but we can live in hope. If we build a spaceship that travels at 1% of the speed of light, our journey of 5.4 light years would still take us 540 years to complete. Realistically, would we ever embark on a journey that takes that long? You'll have your own views, but personally I can't see it happening. It would take 545 years just to get a message back that the spaceship has reached its destination. And if human passengers were to be involved, it would be at least 1,080 years before they, or more probably their descendants, get back to Earth. So, in that light, 5.4 light years is not by any stretch of the imagination an insignificant size. Before we leave this topic, we should consider that 5.4 light years is only just a bit bigger than the 4 light years to Alpha Centauri, and so a journey in our new spaceship would take 400 years to get there. And so we have pretty much the same matters to consider. Would we ever embark on a journey that will take 400 years? If, as I believe not, then into the foreseeable future, travel beyond our solar system will just not be possible. But before we get too depressed, we should pass on to our next topic. Messier 13 is a bright globular cluster in the constellation Hercules. It's a particular favourite of Northern Hemisphere viewers who are denied access to our more southerly globular wonders. It measures 134 light years across. Here I've superimposed an image of it over our background image of the central part of the Eta Carina Nebula, which, you'll remember, spanned 170 light years. To give a better comparison, we should zoom out to include most of the nebula, like so. They say that a picture is worth 1,000 words. 1,000 words is enough to tell a story. So, what story does this picture tell us? That the globular cluster is much larger than any of the star clusters in the nebula? Quite right, it does. but it also tells us how very much larger the nebula is than the globular itself. So you can profitably ponder on these matters, but you can only do so if you know the respective sizes of each. Of course, you'll never see both of the objects in your eyepiece at the same time, but you can still mentally make this comparison when viewing each one separately. Here's a familiar object. It is, of course, the Great Orion Nebula, accompanied by the Running Man Nebula on the left. The Orion Nebula is everyone's favourite. Since it's located near the celestial equator, it's seen equally easily by both northern and southern hemisphere viewers. And it is big and bright, typically filling our eyepiece view. Indeed, it's so bright that larger telescopes can produce some hint of colour at the eyepiece. In our minds, it is a giant in our skies. Here also is an object familiar to us southerners. It's the Tarantula Nebula. The image shows it pretty much as we see it in our eyepiece, with its wimpy little spider arms. But we're not being fair to it. The image of the Orion Nebula was in full colour because it was taken with a long exposure. So we should pay the same compliment to the Tarantula too, like this. Now we can see that it's a grand sight, but is it the equal of the Orion Nebula? Not really, judging only by our two images. But as we did with Messier 13 and the Eta Carina Nebula, it would be interesting to compare these two side by side at the same scale. To do that, we need some data. The Tarantula is located in the Large Magellanic Cloud, some 160,000 light-years away, and measures 1,200 light-years across. The Orion Nebula is 1,344 light-years away and measures about 30 light-years across. Here is our image of the Tarantula, and I've superimposed an image of the Orion Nebula as it would appear to us if it was as far away as the Tarantula is. I could have placed the Orion Nebula anywhere in the image, but I chose this upper right part and labelled it M42. You do see it, don't you? No? Well, perhaps this pointer arrow will help. There it is at the tip of the arrow. In fact, to show the Orion Nebula properly here, it's better to include almost the whole of the Orion constellation as we see it in our sky, like this. You can see Betelgeuse and Rigel and the three belt stars Mintaka, Al-Nilam and Al-Nitak, and because Orion stands upside down in our southern skies, his sword hangs upwards from his belt, and there in the sword, that little red dot, is the Orion Nebula. Now it just so happens that the Orion Nebula and the Tarantula are located at pretty much the same right ascension coordinate. That means that they are both seen in our night sky at the same time, and it's easy and convenient to move from one to the other. So next time that you view them one after the other, it might be helpful to keep this size comparison in mind. Here's a bunch of globular clusters, all captured by the same low-specification imaging system. So they're all accurately displayed at the same scale. I've arranged them in the order of smallest and faintest at the top left to biggest and brightest at the lower right. You can see that the parvoglobular and M55 top the list here. But is the parvoglobular in fact the largest of the group? It seems so in the images, but maybe that's simply a result of its being closer to us than some of the others. What we need is some data. I don't know if you've come across this excellent free program called Where is M13? It allows you to select various deep sky objects, and then it will show you where they're located in the Milky Way. It gives both a top-down view and a side-on view. My reason for mentioning it here is that its underlying database includes both the distance to and the angular measurement of the objects which it lists. So I can use it as a data resource for our globulars. Here is the data that I extracted for each globular. As you know, once we have that data, we can calculate the actual sizes of the globulars. And once we have those, we can rearrange the images into order of their actual sizes. Like so. The smallest is NGC 6397 at 68 light-years, and the largest is M15 at 176 light-years. Who would have guessed that by simply looking at them? Perhaps we can better understand their sizes if we draw some circles around them to suit. It's difficult to say exactly where the boundary of a globular cluster lies, because its stars just gradually peter out into nothing. But I think that this circle here around the smallest of our bunch gives a fair indication of its size. Based on that, the other circles were drawn to the same scale, and you can now see how much bigger M15 is. In our southern skies, we have some truly remarkable globulars. But unquestionably, the king of them all is Omega Centauri. We think of it as being the largest globular in our Milky Way by far. So here's an image of it, taken by the same imaging system, so it's shown correctly to the same scale as the others. And yes, it is very big and bright. So big and bright that it is one of the deep sky objects for which we can get a direct quote of its size from our source references. I did find one source that put it at slightly over 200 light-years across, but most, including many well-regarded websites, such as the ESO, put it at around 178 light-years. But that's only 2 light-years larger than M15. So it seems that Omega Centauri isn't the exclusively large beast that we might have imagined. Once you get into the habit of thinking about the sizes of the objects that you view or image, and maybe perform some related measurements along the way, you may find yourself being led down some quite unexpected byways. So to end this talk, let me turn to this situation that arose back in 2017. In April of that year, an asteroid called 2014 JO25 zipped past the Earth and caused quite a fuss at the time. I wasn't able to get out and view it at its closest approach on the 20th, but I did manage to see it on the next day. It was travelling so fast that it was easy to see it move in front of the background stars. I thought that it would be fun to track its progress by taking a series of 45-second exposures as it passed in front of this galaxy field here in Virgo. I ended up with 26 of them. The next day, I combined all of the images together to produce this somewhat wobbly trail. Now you'll know that modern cameras automatically timestamp their images, so I was able to accurately determine when the first image was started and when the last image ended. That gave me a total imaging time of 1,125 seconds. From the internet, I was able to extrapolate a distance to the asteroid at that time of 3,351,000 kilometers. Since this was my own image, and I knew the angular size of the camera's frame, I could easily measure the length of the asteroid's track to be 17 minutes and 24.5 seconds. And that, of course, let me calculate the length of the track, which turned out to be 16,969 kilometers. Travelling that distance in 1,125 seconds means that the asteroid must have been travelling at 15 kilometers per second, which translates to 54,000 kilometers per hour. But that would be its lowest speed estimate. Our image simply shows the asteroid's proper motion across our line of sight. It doesn't take into account that it was not taken until 1 day after the asteroid's closest approach, by which time it was moving quickly away from us. So our measured distance probably understates the actual distance travelled, and the asteroid's speed was almost certainly greater than our calculated 15 kilometers per second. I did find one reference on the internet to a speed of 21 kilometers per second, which translates to 75,600 kilometers per hour. But let's stick with what we can measure from our image and say that the speed is a minimum of 54,000 kilometers per hour. At its closest approach, the asteroid was imaged by the giant Arecibo radio telescope. It found that the asteroid is a double-lobed object measuring 1.3 kilometers across. Now consider if you were in the path of an object 1.3 kilometers in size, hurtling towards you at a minimum of 54,000 kilometers per hour. I guess that you'd probably have a really bad day. Consider the famous meteor crater in Arizona. It's 1.2 kilometers wide, so it's just a bit smaller than our asteroid. It's calculated that the impactor that created this crater was only half a kilometer in size, and that it was travelling more slowly than our asteroid. So you can imagine how big a crater our asteroid would make, and the impact that that might have on our lives. It's not as big as the 12-kilometer rock that impacted at Chicxulub and wiped out the dinosaurs, but nevertheless, it would leave its mark. Now you may be wondering why we found ourselves down this rabbit hole of doom and gloom. But it all started by being able to measure the size of the asteroid's track and then calculate its speed, etc. Just an example of where considering size may take you. To conclude, let's just quickly review where we have been. If you know an object's size, then you have a much better chance of understanding what you're looking at. And you can then compare it with other objects of similar and not so similar type to better place it into the larger scheme of things. You may be able to get an object size directly from your reference sources, but if you're only given an angular size, you can easily convert that into what you want by employing a little math. To do so, you can use a calculator or you can use software. If you aren't even given an angular size, you can use a sky atlas to measure it, or you can use software to do the job if you have an on-screen image of the object. And you can use software to compare the object with some other object that you may be more familiar with. If you're interested in giving Astrosize a go, you'll find that it's a free download from the website shown up on the screen. And now it only remains for me to thank you for your attention. I hope that you got some fun out of it. If you have any questions that I can't answer, I'm sure that there is more than enough expertise in the room here to help me out. Final note, no formal questions were raised at this stage, but after the talk was over, some people did come up and raise questions and make comments privately.